Welcome to the Rise Inside podcast, hosted by Justin Starbird and powered by Rise Robotics. Listen as host Justin talks to experts from the Rise team about topics relating to mechanical engineering, industrial design, commercialization, and innovation. True collaborations work when ideas are integrated at inception to solve significant problems. Rise Inside brings together how the team continues to work with great folks to commercialize ideas. You're listening to the Rise Inside podcast. Here's your host, Justin Starbird.
Welcome back to Rise Inside. My name is Justin Starbird, and I get to welcome back, now becoming a good friend, CTO, co-founder of Rise, Blake Sessions.
Thanks for having me.
I like doing this. Maybe we should hang out more often.
Yeah. Sounds good.
So, you and I do get to talk about the different things that you get questioned about from either investors or other engineering teams and partnerships. And in business development, they get similar questions about, kind of setting the competitive technology landscape for Rise and what you're actually up against. Can you talk a little bit about that?
Yeah, sure. So there are a number of companies that are really shooting to replace hydraulic systems within heavy machinery. We are not the only ones trying to do that, of course, and they rely on a set number of existing technologies that we can elaborate on. And what we find and what is very common is that these existing technologies that are not fluid power all have their own limitations and issues when it comes to replacing hydraulic cylinders, which are not only incredibly power dense, but also very tough, very safe, and just really well suited to the application. So when we take an electromechanical actuator and try to put it in place of a hydraulic, we have to be very careful and ensure that all of the requirements are met. And it is a dimension in which we excel. We are able to tick all of the boxes, quote unquote, of a hydraulic application. And that's what we're going to get into today.
Awesome. Well, on a previous episode, Toshin James and Emily Heidorf joined us to actually and defined, some of the differences between, some of the technologies that we're competing against. And so today, I'd love to hear more about, how Rise stacks up against a roller screw, a ball screw, the compliant rack and pinion, and of course, what you were talking about, the hydraulic cylinder. First things first. What is, linear actuation efficiency and, why should people care?
Yeah, that's a great question. So it's important because it most directly correlates with a lot of the costs that are associated with building and operating equipment. When you use less power, all of those power systems, all the way from the grid, through the charging apparatus, through the battery side, through to the inverter and the motor, all of that stuff can be downsized if you have a more efficient system. So if you're trying to deliver 10 kilowatts worth of linear power and you have a system that is 50% efficient, then everything is sized for 20 kilowatts. If you have a 25% efficient system, everything has to be sized for 40 kilowatts. So you can quickly see why not only the materials start to spiral out of control in terms of size and cost, but also it is more expensive to operate those devices because they consume more power. So it really, efficiency touches everything from the material use that comes from the ground to the operational cost of operating and owning the machine to the capital cost of the machine itself. And it is really the crux of the comparison between many different technologies. When you're talking about large amounts of power, when you're talking about a few watts, there are times that engineers don't care as much, but when you're talking kilowatts or tens of kilowatts, it really is important.
Sure. Now, do you want to get dangerous and talk about some of the percentages differences between, say what Rise can deliver versus, a hydraulic cylinder or even a roller screw?
Sure. So let's start with hydraulics. Unfortunately, it's hard to be extremely specific because there are many different types of hydraulic system. Most of them that are out in the world today are centralized hydraulic over diesel, which is to say that there's a singular hydraulic pump that generates fluid power and distributes that fluid power across hoses and valves to the cylinders. There are more sophisticated hydraulic systems, often called electrohydraulic actuators or EHAs, that have a pump and a generator in some cases directly, often one and the same, that is directly tied to the cylinder in a way that is local. And those devices are more efficient. In the former case, the centralized hydraulic system, we're typically talking system efficiency between 10 and 40%. And that definition is essentially the ratio of the input power, which in this case is DC power coming from the battery, through to the delivered power, the linear power, which is the product of the force and the speed at which it is moving. Centralized hydraulic systems might run between 10 and 40% overall system efficiency. An electrohydraulic actuator can be much higher. It is typically in the sort of 50 to 60% range. But even with an electrohydraulic actuator, you have in that equation motor losses to contend with, which exist across the spectrum. You have pump losses, you have some often short valve, small valve or hose losses, and then you have losses associated with ports. And all of these are a function of temperature. So the colder it is, the less efficient the machine because the viscosity goes up. Really just unavoidable when you're talking about fluid power.
Sure. And relative to that, what would you say the rise cylinder is a percentage of?
So our drivetrains are well over 90% efficient, and that the ratio that I'm referring to here is the rotational power input coming from the rotational power source, which is often a motor and gearbox, through to the linear power output. So we are well in excess of 90%. And when you multiply that out by a gearbox loss factor and a motor loss factor, which is often, 7% to 20% for a typical high efficiency motor, we're looking at a full system efficiency of somewhere between 70 and 85%.
That's awesome. Another topic that's come up is the volumetric power density and the differences between rise and some of the other potential components that could be used in a solution. Can you talk a little bit about that?
I can, yeah. So hydraulic systems are incredibly power dense, and the way that volumetric power density is measured is the amount of power that a system can deliver divided by the volume that it consumes, which you can define that a few different ways, but it's typically just the diameter of the cylinder squared times pi over 4, multiplied by the length of the cylinder, and there you have at least the approximate contracted volume of that cylinder. So really nothing can touch hydraulics, and I don't want to sugarcoat that. I mean, they are absolutely the most power dense linear actuators on the planet, and they will remain that way, I think, for some time. But we do come close, and the reason that we are able to come close is that the belts that we rely on are able to exert a pressure between the belt and the pulley of in excess of 1,000 psi. So it's close. Again, we aren't quite as compact as a hydraulic, but we're close. There are other technologies that are also pretty good. In particular, a roller screw. A roller screw uses a set of rolling threaded contact mechanics inside of inside of a nut and screw arrangement. I misspoke there. There are no balls in a roller screw. That is part of the whole point. And because you have so many contact patches within a roller screw, you actually can achieve quite a high load density out of those devices.
That's great.
The one downside of a roller screw, well, one of many downsides, is that nut arrangement and the supporting bearings that create the blocks on either side of the rotating screw element are typically very long. So you'll find that the cylinder in the case of a hydraulic is only just a little bit longer than the stroke of the cylinder itself. So if you're looking for a 3-foot stroke, you might end up with a hydraulic cylinder that is 3 foot 6 inches, 3 foot 8 inches, as an example. In the case of the roll screw, you'll find that length addition factor is very, very large, and it has to do with the requirement for all of that additional metal load-bearing structure inside of it.
We've talked a little bit about kinematic precision and how well Rise does with that as well versus hydraulic cylinders. Can you talk a little bit more in depth about that? I
can. So the reason this matters to bring this back to your first point, why do people care? The more precise the device is, often the more easy it is to automate. So you'll find screw systems are really prevalent in industry and manufacturing equipment. They're very precise, far more precise than our systems are able to provide. But that is what renders them to be highly automatable drivetrains. So you have a repeatable, quick, precise, repeatable interaction every time you choose to move the screw. By comparison, you can't rely on the same methods to obtain position for a hydraulic system. You can add methods of obtaining position based on linear potentiometers or linear encoders, but it is essentially impossible to measure the integration of volume dt and expect to get an accurate position output from that. So combined with the complexity of a fluid power system in terms of how fluid is distributed and where it goes and how often it goes there, you're essentially limited to measuring the output, which works. But nonetheless, the overall package doesn't necessarily result in a highly precise device. And again, precision results directly in automation ability.
And another thing that you talked about a little bit ago was the length of stroke. So what is the max stroke for a rise cylinder relative to some of the other technologies?
Yeah, so that's a good question. So hydraulic cylinders are particularly good at achieving long strokes. You can essentially make them at any length, and some of them get quite long, in some cases dozens of meters. We are equally capable of achieving nearly any stroke you can imagine, whether it be 2 meters or 20 meters. Our methods scale in a line very easily. So we're not constrained by a manufacturing method nor a kinematic issue with our ability to scale length. By comparisons, screws, both roller screws and ball screws, have an issue to contend with that is called critical speed. And what that means is that as you spin the screw, it starts to become unstable, and there is a speed beyond which it will essentially whip out of alignment and cause immediate damage. So it's an issue that's easy to avoid. This critical speed is a function of the size of the screw, the length of it, the relative rigidity of the blocks that mount the screw to the fixed part of the device. But nonetheless, the screw cannot be run faster than usually about 70% of that critical speed. And what that results in is a limitation of the net stroke that the screw is capable of doing. So screws are often limited to either 1 meter or 2 meters. Again, it is possible to find screws that are longer, but it means they might have to run more slowly, or it means they might have some other custom aspect of their design that isn't conventional.
Let's talk a little bit about tolerance, both the shock tolerance and then, side impact tolerance of the rise cylinder. How does that measure up right now?
Yeah, this is a really important point. So hydraulics are notoriously good at dealing with shocks, and it sort of makes intuitive sense as to why that's the case. There's no metal surfaces that are being loaded up as a result of direct axial shock. In a similar vein, our systems have these belts that are slightly elastic and are able to sort of give and take small amounts. They usually stretch about 0.5% under full load, which is quite similar to the amount that fluid will expand and contract when it is loaded and unloaded. So we have a similar level of kind of inherent shock tolerance in the linear drive itself. And when you combine that with methods of shock prevention and shock assistance that are applied directly to an individual section of belt, we can obtain a system that is quite resilient in a way that is analogous to having a pressure relief valve on a hydraulic system. If you compare that to screws, it is possible to make these things series elastic, but if you don't, what you'll find is that you have direct metal on metal contact mechanics that when you overload them in axial compression with an impact load, you'll dent the bearings and the races, and once they're dented, they're done. So it only takes one high shock event to really destroy the entire system, and particularly in cylinders that find a wide variety of use cases, it's almost impossible to prevent.
We've talked a little bit about, and we definitely talked with Emily and Toshin previously about the placement of the pump and drive, system, and how difficult it is to, work with a lot of hydraulic systems. How, what does that mean for Rise, and what have you done to overcome that?
Yeah, so that's another really important point to bring up. All of these are really factors that either make or break an application in terms of its feasibility. Like, can we even fit this into the machine? Will it last? These are really questions that are independent of cost. They're simply, will it work? Right. That's why we're excited to be here, because we're solving those.
Right. That's what I was going to say. That's why we're here. This is why we get to have these exciting conversations.
Right. So one of the best things about hydraulic systems, as most of us know, is that you can place the motor and the pump remotely and simply run lines out to the peripheries of the machine where the action is happening. So in addition to the cylinders themselves having very high power density, the method of routing power to them is also quite dense, quite compact in the hoses themselves. But it's a blessing and a curse, and hydraulic hoses have a ton of drawbacks. On the maintenance side, also the pressure loss across the hose. I'm not sure anybody really enjoys replacing hydraulic hoses. That isn't the point. But nonetheless, it results in the ability for the designer to design the most compact thing possible, which is really nice. Now, when you compare that to screw technologies, screws have the motor and the gearbox packaged right at the end of the cylinder. So in addition to the device being longer than you might hope for, usually whatever the stroke is, plus a much more significant length than you would otherwise expect for hydraulic, you have the motor and the gearbox to contend with to add to that packaging difficulty. So that's, in some cases, it can be accommodated. In most cases, it can also be a deal breaker. And we've seen ourselves, we have some implementations of Rise Cylinder that also have that same packaging, and it can be really tough. The compliant rack and pinion that is designed and made by Cascade Drives has an even worse packaging situation in their case, which is they have a large motor and gearbox assembly that is essentially at the distal end of the cylinder, right in the middle of the action of the device. And it just has to do with the fact that the pinion set is the acting load carrying element, and you have to place it at the distal end of the cylinder, the far end of the cylinder, in order for it to work the rack back and forth. And as a result, you have the largest possible mass that you would normally have not at all with a hydraulic system in the worst possible place. So one of the benefits of working with a Rise cylinder system is that you can route the belt from the linear unit, the actual cylinder drive unit. You can route the belt short distances to a location that is more convenient for the belt power unit, which is where all of the actual work is done in a way that is analogous to a hydraulic power unit. It really simplifies that packaging challenge.
Another solution that you've, by going this route and by really creating the cylinder in itself, you've reduced environmental impact. You talked a little bit about hoses. You've talked a lot about oil and different fluids. Can you talk a little bit about that impact and how that compares?
Absolutely. So it kind of runs across the gamut from material use. We have far and away the lightest linear actuation solution possible. So we use the least amount of material, which is a direct savings both to the bottom line and to the planet. By virtue of having the most efficient machine, we waste the least energy, which obviously has a huge environmental impact. And then, of course, we simply don't rely on hydraulic oil. And I think we all know the issues associated with oil use. And this isn't to say that other electromechanical actuators don't also have those advantages. They absolutely do. But I think purely from the material use perspective, we are still in the lead in that regard.
Absolutely. Another one that we've talked about is actually component, and that's the seal robustness, within the unit. Can you talk a little bit about the function of the type of seal?
Yes. So there are a few different types of seals. To start with hydraulics, just to kind of set the scene here, we have two main seals, and additionally a wear band, which really isn't a sealing element. But let's talk about the two main seals in hydraulic. One is a pressure seal, which keeps the fluid from leaking from chamber to chamber, of course. And then the second is an excluder, which is often at the interface between the rod and the housing, and it's what is used to keep material out of the cylinder, to keep dirt and other material from entering the cylinder. So one is used to prevent egress of oil, and the other is used to prevent ingress of particulate and contaminants. The issue with that is that you can't see the seals with your eyes once they're in service. And to my knowledge, there isn't an automated way of measuring seal wear. Obviously, you can predict and you can run calculations, but you don't know the condition of the seal. And once it's lost all of its spring capacity to seal up against the housing, seal is done, right? So because the seals are under pressure, in the case of a hydraulic system, the fluid itself packs the seal into the running surface in question. So it basically forces contact between the rubber seal and the housing of the unit, and thus adds extra pressure to the friction surface itself. And that's why, while hydraulic cylinders are very good and very well sealed in that dimension, usually against a hard chromed shaft, because they're under pressure and because they fail in such an aggressive way when they when they do run out, I think we can more or less acknowledge that they are well sealed, but not perfectly, just because, that's what it is.
Right.
So by comparison, our cylinder is, and also the same benefit applies to screws. We have an excluder seal. We're not containing pressure, so we don't have to worry about that high pressure acting on the sealing element itself. It's just there to keep material out and to keep ingress from happening. And then the one other point of comparison here would be to the compliant rack and pinion type drive, where we consider the environmental sealing of that device to be relatively poor. And the reason for that is that because the rack itself has teeth on it and it isn't a round rod by nature, you can't seal against it. And so what they're doing is simply placing a bellows around that device that just acts as a bellows. And as long as that bellows remains intact, I mean, sure, you technically have a boundary between the environment and the internal working surfaces of the rack and pinion, but any foreign debris or impacts or really anything that touches that bellows degrades it. If the material cracks or wears eventually, once that bellows is gone, it's toast. So really the only proper way to seal a linear actuator, in my mind at least, is to use an excluder or a wiper seal, and that is what screws and Rise systems both are able to deliver.
Yeah, another environmental impact is, for a lot of industries that you're touching right now, is in and around temperature and ranges of temperature, because some of the heavy machinery that you're potentially working inside of is going to be working in really cold environments, or in some cases really hot environments, really warm. Yeah, tell me a little bit about how Rise handles different temperatures.
Yeah. So hydraulic systems are pretty well suited to work across the temperature range. At the colder temperatures, they often include heating systems that warm the oil to a point of usability. So that's a separate additional system sort of level requirement that gets added in for cold weather. But certainly there are hydraulic systems that operate in every possible environment from -40°C up to +50 and above. So our systems rely on polyurethane belts that are rated down to -30°C and up to +50. So we take the vast majority of that range and are able to work within it. When you compare that to screw technologies, in particular to roller screws, the complexity of the metal to metal interaction within the screw nut interface limits your ability to expand or contract those materials in significant ways. So most roller screws are limited to a lower limit of about 0°C, about freezing. You can store them in lower temperatures, but usually it is not recommended to operate the device under freezing. Ball screws are a little bit better, but again, you still have limitations where as you start to run into very low temperatures, you see changes in the relative geometries of the metal load-bearing structures, and that results in a potentially shortened service life.
Another area of surface life is the stiffness along the axis. Tell me a little bit about what that means and how that impacts Rise.
Yeah, so this one is kind of tied in with kinematic precision. I think we covered that one pretty well in the sense that hydraulics are fairly compliant and it makes them tough, but it also makes them hard to control. That thickness does really serve screws well. Ball screws find utility in industrial applications, in many cases for their stiffness, for their high stiffness. If you want to produce a very high frequency response or vibration, a linear vibration, really the only way to do it is with a screw. So our systems don't really compete that well in that regard. We're not the stiffest option out there, and we don't claim to be, but it is stiff enough to serve in a hydraulic replacement application.
Absolutely. Well, the last two components that I want to talk about are, inevitably the ones that are most discussed and where you get, the most, I don't want to say questioning, but certainly people want to know about cost and they want to know about maintenance and how that measures up, because, by and large, folks are used to, preventative maintenance or waiting for something to completely blow out before they replace anything. And in either case, there's a significant cost associated with both of those, possible solutions. And really it comes down to the company or the personnel mindset of how they address it, especially related to hydraulics. So I saved those two, for you to kind of answer in tandem, because a lot of times you can't get away from maintenance without cost, and a lot of the cost is part of the maintenance. So we've had now a couple of times where we get into it. From your perspective, how do you help partners and clients answer those?
I think to start with the maintenance, we have, I think the best way to kind of understand it is that our materials are solid state. So instead of having working fluids that are circulating around a system, I think about the maintenance required on my car. I mean, I drive a Tacoma, and it has maybe 5 or 6 different fluids. We have transmission fluid and differential, brake fluid, obviously engine oil. Each of these fluids requires replacement or inspection at some point in time, and is often fluid service that is the most expensive type of service to perform. I mean, obviously, replacing an engine is also expensive, but for the most part, regular maintenance, in the category of regular maintenance, fluid maintenance is one of the most expensive things. It's also the most environmentally destructive and the most wasteful. So simply by just doing away with oil in its entirety and by relying on solid state components that are treated well, we can dramatically reduce the maintenance requirements. And as we've touched on, both in this conversation and elsewhere, we monitor our materials continuously for signs of degradation and wear. So we know before the material has ever come close to the end of its service life, we know in advance that it's headed there. And as a result, we can be more intelligent about how we plan maintenance intervals and actually service the machine when it is really needed, and not before or after, both of which have their own issues. And then to touch on cost, I think just long term, when I look at the way that power is distributed within a piece of heavy machinery, I don't see a future in which electric distribution is not the norm, which is to say, even for systems that have hydraulics, they're going to be pushing more and more towards EHAs, electrohydraulic actuators, which is to say, distribute the power electrically, get the power out to the periphery, to the point of action, and then turn that electric power into linear power by virtue of an EHA or an EMA or a RISE system, whatever the case may be. And so it really comes down to the challenge is really a subset of how I framed it a minute ago, which is how do we get rotational power from a motor, because it was delivered to that motor via an electrical bus, and translate it into linear power at that point of action, right? So what is the cheapest way to get rotational power into linear power, I think is one way to frame the challenge here. And electrohydraulic actuators do it with a motor and a pump and a cylinder. We do it with a motor, in some cases a gearbox, and our linear belt drive. Screws do it with a complex screw type interaction, nut and screw interaction, rolling basis. Really, nobody's considering lead screws for any of these applications. It's not on the table. So again, it comes down to that simple question: how do we get rotational power from a motor shaft and translate it into linear motion in the most cost-effective way possible? And we've just found through repeated experimentation and research that what we're doing in terms of getting that rotational power from a motor shaft and translating it into linear power, it's cheap, it's lightweight, it's relatively simple, and all of the precision components are contained within assemblies that are relatively tolerant with respect to each other. So if you apply a side load to a cylinder, you're not directly impacting the precision interactions within the bearings, because those are kept on separate tracks, which is not the case for screws. In a screw, if you apply a heavy side load, you are physically changing the distribution of stresses within the screw nut interaction itself. So all of these things taken together, we're simply using the fewest components. We're using the most conventional machines to produce our components in terms of using CNC lathes. We don't need to go to high precision kind of esoteric machines that are used to make our stuff. And all of that kind of results in low cost and low material use at the end of the day.
That's awesome. I love how it's not easy to go through each of these differences, but I think it's really important to discuss the competitive advantages that Rise offers, and it's not just that. A lot of these things are a lot more technical in nature than people give it credit for, right? And so I think the way you've broken everything down here is going to be really helpful for folks to understand what Rise does, how you do it, and really how it can apply to their application.
Great.
Well, thank you so much, Blake. I really appreciate it. Anytime you want to do this again and take some time to explain something to me, by all means, I'm all ears.
Great. Thanks for having me, Justin.
You have been listening to the Rise Inside podcast, presented by Rise Robotics. On behalf of our guest today and host Justin Starbird, thank you for listening. Please share your feedback on our LinkedIn page, linkedin.com/company/rise-robotics.